Hello. The global financial crisis of 2007 to 2008 was a worldwide economic crisis. Some banks defaulted, others were bailed out, and stock markets fell by around 40 to 50%. In more exotic corners of the financial markets, the moves were even more substantial, and it was in the context of losses resulting from these moves that David Viniar, Goldman's chief financial officer at the time, was quoted as saying, "We were seeing things that were 25 standard deviation moves several days in a row." Now, if you've studied maths at high school, you may have looked at the probability of 1, 2, or maybe 3 standard deviation moves. But 25? It really does seem like a big move. And that raises the question, how likely is a 25 standard deviation move? That's what we're going to look at today. It turns out to be a rather interesting problem. Firstly, we'll realise that the question doesn't really make sense as it stands. Then, our answer will involve an integral which cannot be expressed in terms of elementary functions. That will lead us to a series solution, only to find that it doesn't converge. And finally, we'll end up with an expression that your calculator is unlikely to be able to evaluate. It's too small. Nevertheless, we are going to find a very good approximation to the answer, using nothing more than a scientific calculator and our brains. Let's start by considering two distributions. X is normally distributed with mean 0 and unit variance. Its probability density function is 1 over root 2 pi e to the minus x squared over 2. Variable y is uniformly distributed between -1 and 1, so has the probability density function of 1/2 in that range and 0 elsewhere. Now clearly x has unit standard deviation. Let's find the standard deviation of y. Well, the expectation of y is given by the integral of y times the probability of y dy, which is the integral from -1 to 1 of y times 1/2 dy, and that's 0. The expectation of y squared is given by the integral of y squared times the probability of y dy, which is the integral from -1 to 1 of y squared times 1/2 dy, and that's equal to 1/3. So the standard deviation of y, which is the square root of the expectation of y squared minus the expectation of y, all squared, is equal to 1 over root 3, and that's equal to 0.577. Now let's consider the probability that x is greater than 1 standard deviation above its mean. Well, we know from high school that the probability that x lies within 1 standard deviation is 0.68. So the probability that x is greater than 1 or less than 1 is 1 minus 0.68. Both tails have equal probability, and therefore the probability that x is greater than 1 is 1/2 of this, which is 0.16. Similarly, the probability that x lies within 2 standard deviations of the mean is 0.95. So the probability that x is greater than 2 standard deviations from the mean is 0.02. Let's do the same for y. The probability that y is greater than 1 standard deviation is the integral from 0.577 to 1 of 1/2, which is 0.21. The probability that y is greater than 2 standard deviations is 0, since y cannot be greater than 2 times 0.577 because it's greater than 1. Now let's compare the probabilities for x and y. Y has a greater chance of being above 1 standard deviation than x does, but that reverses when we look at a 2 standard deviation move. It's not even possible for y. What all this illustrates is that it doesn't make sense to talk about an n standard deviation, in particular a 25 standard deviation move, without reference to the underlying distribution. For several reasons, if the distribution isn't mentioned, then it's assumed to be normal. So now we can refine our question. We are looking for the probability that x is greater than 25, given that x is n01, which is just 1 over root 2 pi times the integral from 25 to infinity of e to the minus x squared on 2. We'll write that as 1 over root 2 pi times I. Unfortunately, I cannot be evaluated in closed form. In fact, if you stick the expression into a scientific calculator that does numerical integration, that won't work either. Try it and see. What we can do is to use a trick to evaluate I. We write it as 1 over x times e to the minus x squared on 2. We then use integration by parts, differentiating 1 over x and integrating the rest. Now the indefinite integral of x e to the minus x squared on 2 is just minus e to the minus x squared on 2. Consequently, I evaluates to e to the minus 25 squared on 2 over 25 minus the integral from 25 to infinity of 1 over x squared e to the minus x squared on 2. We'll label the latter integral as E1. From here, we can do two things. Firstly, we can observe that E1, by virtue of the 1 over x squared term, is at least 25 squared times smaller than I, so we can ignore it, giving an approximation for I which will have a relative error of about 1 over 25 squared, which is about 2 times 10 to the minus 3. The alternative is to write the 1 over x squared term as 1 over x cubed times x and integrate by parts again. This gives us equation 3. This time, the integral on the right, which we label E2, is even smaller. By virtue of the 3 over x to the 4 term, we know that E2 is no bigger than 3 over 25 to the 4 times I, i.e. a relative error of about 8 times 10 to the minus 6. Again, neglecting E2 gives us a better approximation to I. The alternative is to keep on integrating by parts to get a series expansion for P. But there's a problem with this result. If we look at the ratio of successive terms, we get minus 1 over 25 squared, minus 3 over 25 squared, minus 5 over 25 squared, and so on. Not only does this become less than minus 1, it tends towards minus infinity. Therefore, the sum will initially start to converge, only to diverge as we add too many terms. Fortunately, the error of about 8 times 10 to the minus 6 by retaining just the first two terms is good enough for us. If we put the approximation of equation 2 into a calculator, we hit another issue. The calculator returns 0 because they can typically only represent numbers as small as 10 to the minus 100. To get round this, we take logs to the base 10 of both sides. A calculator can cope with that and gives about minus 137.514. We write it as minus 138 plus 0.485. We then exponentiate both sides to the base 10. This tells us that P is 10 to the minus 138 times 10 to the 0.485. We evaluate the second term in a calculator to give P equals 3.0615 times 10 to the minus 138. Doing the same with the approximation of equation 4 gives P equals 3.05667 times 10 to the minus 138. The exact result is 3.05669 times 10 to the minus 138. So as we expected, our approximation is very good. To put this number in context, bear in mind that the universe is only about 4 times 10 to the 12 days old. In other words, we would not expect a single 25 sigma event to happen even once since the beginning of time. So what do we conclude? Well, firstly, the distribution of the event was not normally distributed. Any model based on such an assumption must be incorrect. Secondly, no matter what model was actually used, the probability of the event happening is much greater than a 25 sigma move on an assumed normal distribution would suggest.